We absorb, Wait, I think I have some Lego Weekend toys from back when I was like 4. Yeah, exactly.
All right. Anyway, let's take a look at 192. Yesterday we were exploring how we can use different graphical capabilities of the calculator, the rational root theorem. We can use the quadratic formula or factoring. Okay, all these different methods or techniques to our advantage to help us find every single x-intercept we might have, whether if it's positive, negative, zero, imaginary, any case. So we're going to do a little bit more with that today. The thing is, the ones that we were doing yesterday were very kind of straightforward. The questions kind of guided us as to what we should do for each and every step, if you will, but they're not always going to look like that. For instance, if you look at number 1 and number 2, the directions are to just find every single x-intercept. Find all roots. So we're not going to have those guided or skeleton type questions to help us get there. Okay, it's going to be up to us to figure out how to do this. So what I want to do is just briefly take the time to develop a plan of attack on how we kind of did this yesterday. Can you reference the 3 examples from yesterday and try to think about what we did for each one? They were all relatively the same. It's just the results that were a little different. Yeah?
Start by trying to factor.
Can you factor? Okay. That saves you some time, okay? I think if you thought about factoring, at least the ones we had yesterday were maybe 4 terms, sometimes even 5. So we can't factor 5 terms, and if we have 4 terms, we could try grouping, but at least in this example, that's not going to work because 3 and 8 will never match 13 and 6. Okay, so can you factor? At least that's a question to ask. Okay, more often than not, though, just to give you a heads up, the answer is going to be no, because we're going to try to use some of these other techniques besides factoring. So if your answer is no, where can we go from there? Go, Noah? Graph it. Okay, so either a graph will be provided. We had that available to us yesterday for some of them. But for the 2 we're going to do today, the graph is not provided. So let's graph it. And once we have a picture of it, what should we try to analyze about that picture? What would be useful to figure out or kind of know? Yeah? The type of what? Function? Okay, well, we can tell that based off the equation, like if it's cubic or quartic. What's the type of function leading us into, though, in terms of the x-intercepts? If you know it's cubic, how many x-intercepts? Or multiplicities, rather. 3. If it's quartic, 4. Okay, so we're going to graph it, and then we're going to find where the x-intercepts are located. And then we'll see what the combinations are. Okay? Do we have one positive x-intercept? Do we have a negative x-intercept? Do we have any possible imaginary ones? Do we go through the origin, aka an x-intercept of 0? Okay, we're going to see what the exact combination is that would fit this power or type of function like Julia said. Okay, so graph it, find x-intercept, and see what the combinations are. Then what can we do? Good enough?
Find the possible roots.
Okay. Find possible roots. We're going to develop that list. Sometimes it's small, sometimes it's long. Okay, find possible roots by using the rational root theorem. Okay, that's with all the pluses, plus and minuses. Once we develop our list, how can we see if one of those possibilities is actually a root or not? How can we test it? Synthetic division. All right, so synthetically divide to verify a root. We're looking for a remainder of 0. So after we get done synthetically dividing everything, sometimes we might have one number to check, maybe we have 2, maybe we have 3, it all depends on the graph, okay, what it looks like. Once we get done dividing, where can we go from there? This is what was kind of new to us yesterday. Yeah?
Find the imaginary roots.
Okay.
Or like, not real numbers.
Find imaginary, or I think the other one you're trying to say is irrational.
Yeah.
Okay, non-fractional ones, like square root of 3, square root of 10. Find imaginary or irrational roots by doing what? Yeah? By rewriting and solving the quotient. Okay, what's left over from that synthetic division? Perfect. Okay, plan of attack. We did all of that yesterday. We just wrote it down in words today. So we're going to use those like 4 or 5 things to help us with these 2 today. So we can use this as a guide. So taking a look at G, got to ask ourselves, can we factor? If the answer is yes, we're going to do it because that's going to take us immediately to the roots. We're not going to have to worry about any of these other things. Unfortunately, I think we already discussed this a little bit. The 4 terms, we try grouping. There's no way a 3 and an 8 can match a 13 and a 6 like it would need to do for the grouping technique. So factoring is a no-go. So let's go ahead and graph this function. We're going to get a picture of it, and we're going to try to identify where positive x-intercepts are, negative ones, maybe imaginaries. We'll see what our combination is. So on a calculator, there should be some around on the desks, or maybe you can work with a partner. We're going to try to graph it. 3x to the 3rd plus 8x squared plus 13x plus 6. Before you hit graph, check your window. Right now, mine's set to -3 and +3, -15, +6. I don't know if this is going to be good or not. That's just what it is right now. All right, let's hit graph to see if it's good enough. I think that's pretty good. We can see an x-intercept, right? No need to change it. So based off the way that graph looks, can we list how many positive x-intercepts we have, how many are negative, how many are at the origin, how many are imaginary? Bless you.
Thank you.
Let's see, I don't see any x-intercepts on the right-hand side, so I'll put 0 for positive. I see 1 x-intercept because it goes straight through, multiplicity of 1 on the negative side. I do not go through the origin at all or touch the origin, so I'll put 0 there. What about imaginary? 2? I'm hearing whispers and seeing the peace sign. 2? Okay. Our function is cubic, so we should have a total of 3. So 1 and 2 look good. Okay, so from there, okay, we developed our combination. Looks good. We're going to find the possible roots by using the rational root theorem. So we're going to try to figure out what this x-intercept is. Perhaps the one that we graphed. Maybe it's a fraction, maybe it's not. We don't know. We're going to test it. So based off the equation, we need factors of 6 divided by factors of 3. Let's see, 1 over 1, 1 over 3, 2 over 1, 2 over 3, 3 over 1, 3 over 3 is already listed, 6 over 1, and then 6 over 3 is already listed. So 1, 2, 3, 4, 5, 6 times 12, 12 options. Okay, a little less than the ones that we've seen in the past, which isn't bad. So looking at the graph, can we kind of perhaps circle which one of these this x-intercept might be? Can we narrow it down? What do you think, Elsie? Negative 2/3? Okay, let's try it. 1 doesn't make sense because we don't go through positive 1 or negative 1. We definitely don't go through positive 3 or negative 3. We don't even have 6 graphed. We don't go through positive 2 or negative 2. So the only ones that are really left are 1/3 and 2/3. And since that x-intercept seems fairly close to negative 1, the 2/3 makes a little bit more sense than the 1/3. Okay, it's a bigger fraction. So we'll go ahead and test negative 2/3 using our synthetic division. All right, drop the 3 and then you can go ahead and divide. Looks like we were right. All right, so we synthetically divided to verify a root. We've just proved that negative 2/3 is the exact x-intercept. So we found this negative root that we listed from our combination. We now have to try to figure out where these two imaginary ones are. So we're going to take the quotient and see if we can take that any further. Now to help us out, we should really take this coefficient or these quotient numbers and divide by 3 to make them 1, 2, and 3. Putting the x's back in, we'll have x squared plus 2x plus 3. And we're going to set it equal to 0 to help us figure out these other x-intercepts. How do you want to solve for x in this case? What do you think, Lainey? Okay, can we think of two numbers that multiply to 3, positive 3, but add to a positive 2? No. 3 and 1 seem like they should work, but the 1 would have to be negative, right, to get here. But 3 times negative 1 would be a negative 3. So if factoring doesn't work, what could we do? Our favorite quadratic formula. Let's do it. All right, opposite of b, so negative 2, plus or minus b squared, 4, minus 4 times 1 times 3, be 12. All over 2 times 1, which would be 2. All right, so negative 2 plus or minus the square root of negative 8 all over 2. Notice how the square root on the inside is negative, so this is definitely going to give us those two imaginary ones that we were looking for. So it seems like we're going in the right path. Let's see if we can keep this going. Can we figure out what the square root of 8 is? It's not a whole number, but can we simplify it? Can we rewrite it? Are we familiar with this? Yeah.
You could do square root of negative 4 times square root of 2.
Okay, so you can rewrite the square root of negative 8 as the square root of 4 times 2. I'm going to ignore the negative because we know that's just going to be an I. What's the square root of 4? 2. And then the square root of 2 is unknown. Well, not unknown, but it's not a whole number. So you can rewrite the square root of 8 as 2 square roots of 2. And since the 8 was negative on the inside, we know we're going to need an imaginary I. And that's all over 2 on the bottom. So we have all these 2's going on, so we should be able to divide. If we do negative 2 divided by 2, that'll be negative 1. And then we're going to take the 2 in front of the square root, and we can divide that 2 away. So 2 divided by 2 would just be 1 as well. So we're just going to be left with a square root of 2i. All right, so let's go ahead and list our x-intercepts. We have the negative 2/3 that we verified from the synthetic division. And then by looking at the quotient further, we found our 2 imaginary ones. We'll have negative 1 plus square root of 2i, and then negative 1 minus square root of 2i. We doing okay from yesterday? Should I take the silence as a yes? Yeah? Okay. It's beside it. Yeah. It's beside it. It's not under it. If you want to write it out front, you can. Like I squared root of 2, if that's easier. Okay. So you know it's not under it. All right, let's go ahead and try our last one. We definitely have 5 terms here, so factoring is kind of out of the question. We haven't discussed factoring 5 terms. So let's go ahead and graph it. Bless you. All right, I'm going to hit graph. I have the same window. I don't know if it's going to be good or not, but we'll see how it goes. All right, I say that's pretty good. We can see the x-intercepts. So based off the graph, let's list how many are positive, how many are negative, how many at the origin, and how many might be imaginary. We have 1 positive on the right side, 1 negative on the left side. We don't touch the origin. So imaginary possibilities? How many? 2, okay, because we're quartic. Looks good. All right, so now that we have our combination, let's go ahead and see if we can figure out where some of these positive or negative ones are using our rational root theorem. We're going to need factors of 3 over factors of -6. So it looks like we're going to have the same numbers as previously, just flipped. All right, so plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6. Then we'll move on to 3 up top, plus or minus 3, plus or minus 3 over 2. 3 over 3 is already listed, and 3 over 6 is already listed. So looks like we have that list. Not as big as the other ones that we've seen. So looking at the graph, can we try to reason through as to which ones on this list might fit the ones in the picture? We don't go through 1 or negative 1. We don't go through positive or negative 3. Can we circle some possibilities? What do you think, Caitlin? Negative 1/3. Okay, so this one right here, it definitely doesn't look like it's halfway, so we'll cross off the half possibility. And then 1/6, I would guess, would be closer to the origin, okay, kind of a small decimal value. So I would agree that the 1/3 kind of makes the most sense out of those fractional lists or possibilities. So then this other one looks like to be exactly halfway between 1 and 2. So that would be 3 halves. Let's go ahead and test those. Let's do negative 1/3. Looks like that one works. We'll go ahead and divide our quotient by 3. That way when we test 3 over 2, we have some smaller values. If you forget to divide the quotient, that's completely okay. It'll still work out. You just might have larger numbers to work with. So don't feel like it's the end of the world if you can't remember to do that. So we'll have negative 2, 1, 1, and then 3. Looks like that one works as well. Keep in mind, we should really divide this quotient by 2. If you forget to do that, it's okay. So we confirmed that negative 1/3 is our negative root, and positive 3 over 2 is the positive root. Let's go ahead and take our quotient further to try to figure out these two imaginary ones. Can I erase this x-intercept list at the bottom? Because I'm running out of room. Is that okay? All right, so if we divide our quotient by 2, negative 1, negative 1, negative 1, we'll have negative x squared minus x minus 1, and we'll set it equal to 0. How do you want to solve for x? You want to take a negative out? You can do that. We'll take out a negative, that'll make everything positive. If we tried to factor, can you think of two numbers that multiply to 1 but also add to 1? No, so factoring is not an option. Quadratic formula, okay? I'm not sure if you guys are noticing a pattern yet or not, but the imaginary ones, more than likely you're going to have to use the quadratic formula. Okay, sometimes you won't have to. I think the second example that we did yesterday was a case where we didn't have to do the quadratic formula, but if they're imaginary, keep in mind that's always a possibility. So let's go ahead and try that. We need the opposite of b. So since we took the negative out, our b value would be 1. Opposite of that would be negative 1. Plus or minus square root b squared would be 1 minus 4 times 1 would be 4. All over 2 times 1, we'll get 2. So x equals negative 1 plus or minus square root of negative 3 all over 2. And we can write that as negative 1 plus or minus I square root of 3. I'll put the I out front just so you know that it's not underneath the square root. And that's all over 2. Now, we cannot simplify the square root of 3 like we did the square root of 8 in the previous example. So you can leave it exactly like this. Okay, you can't really divide the 2 out because we don't have some divisible values there. So if we go ahead and list the x-intercepts, we verified negative 1/3. We verified positive 3 over 2. And if we write the two imaginary ones, negative 1 plus I squared root of 3 over 2, and then negative 1 minus I squared root of 3 over 2. Okay. You can leave them as fractions. I know previously we divided it through because it would work nicely, but you can leave them like that if you don't want to divide. Okay, it means the same thing. We doing okay? All right. We're officially done with 2.9. Monday and Tuesday we'll take a look at 2.10, which is just a little bit of kind of a review section, bringing everything together.
Mrs. Bauer, could I object on password today?
You can.
Thank you.